Hey everyone, let's jump right into this explainer. Today we're doing something a little bit different. We're skipping the basic syntax tutorials. You already know how to write a simple PyTorch script, right? Instead, we're going totally under the hood. We'll be using insights from the O'Reilly guide, Programming PyTorch for Deep Learning, to deconstruct the dynamic mechanics of what actually happens when your code runs.
Because, honestly, what really happens to your memory and your gradients when you hit run? Anyone can copy and paste a training loop from a forum, but when your model suddenly throws an out-of-memory error, or your gradients just mysteriously vanish into thin air, well, knowing the raw, invisible mechanics driving those tensors is exactly what separates the novices from the absolute experts.
Okay, let's kick things off with Section 1, the eager execution paradigm.
So, right out of the gate, PyTorch operates on this define by run paradigm. Think about traditional static graph frameworks where you have to rigidly declare your entire network structure before absolutely anything runs. PyTorch doesn't do that. It literally builds its computational graphs on the fly during the forward pass. This eager execution paired with tape-based differentiation is a total game changer. It means you can dynamically alter your architecture mid-flight, and PyTorch just naturally adapts. It's basically like building the train tracks while the train is already moving.
And this paradigm completely shifts how we need to think about tensors. As this quote perfectly captures, a tensor isn't just some passive multidimensional array holding your pixels. It's a functional, living piece of your network. It inherently carries the mathematical rules required to interact with other tensors. So when you operate on a tensor, you're not just crunching numbers. You are actively tracing a path on a dynamic computational graph. Moving right along to Section 2, tensor mechanics and memory.
Now, one of the most powerful tricks PyTorch does under the hood is tensor broadcasting. It effortlessly applies operations across totally mismatched tensor shapes by following a few strict rules. It checks the dimensions starting backward from the trailing dimensions. If they match, or if one of them is just a 1, PyTorch dynamically expands it for you. This is absolutely crucial because manually expanding tensors before matrix operation is a wildly slow, memory-hogging nightmare. But as we're squishing and stretching these shapes, we have to talk about memory. To avoid those dreaded in-place memory errors, you've got to know the difference between .view and .reshape. Here's the deal. .reshape is like your safety net. It handles contiguous memory chunks automatically behind the scenes. .view, on the other hand, demands a strict, unbroken block of memory. If your tensor's data is scattered all over your physical RAM, .view is just going to crash your program. Grasping this prevents hours of ripping your hair out while debugging. Which brings us to a massively common pitfall, the memory leak trap. Okay, imagine you calculate your loss for a batch. That tiny loss tensor is actually still tethered to the entire history of your computational graph. If you just add that raw tensor to a running total to track your epochs, you are literally trapping the entire graph in your RAM for every single step. It builds up fast. The fix? Just use .item. Calling .item safely severs that tether, pulling out a standard Python float and completely saving you from a massive memory leak. All right, let's dive into Section 3, deconstructing the training loop. So here it is, the absolute core heartbeat of your network. This 5-step blueprint is the mechanical cycle required to train basically any PyTorch model. You zero out the old gradients, push the data forward, calculate how wrong you were, compute the backward gradients based on that exact error, and finally, have the optimizer physically step the weights in the right direction. And when you step out of that rhythmic training loop to actually test your model, you must mechanically shift gears by calling model.eval. Now, a lot of people mix this up, but it's totally distinct from torch.no_grad, which just turns off gradient tracking. What model.eval actually does is freeze the specific behaviors of layers like dropout or batch normalization. If you forget this, your model will just keep randomly dropping nodes during your test phase, completely ruining your predictions. You really need both, model.eval to lock layer behavior and torch.no_grad to save memory. Let's move on to Section 4. Optimization and the Autograd engine. Think back to step 1 of our loop, 0 grad. Why is it step 1? Well, because PyTorch is designed to accumulate gradients by default. If you skip this, the Autograd engine will just infinitely pile new gradients on top of the old ones from every past batch. You'll instantly break your derivative math, and your model will absolutely fail to learn. To really visualize what's happening mathematically, think about navigating a complex loss landscape. When you call loss.backward, the Autograd engine traces the derivative tape backward to get your gradients. Then, the optimizer uses those exact gradients to chart a physical trajectory across this undulating landscape, sliding down from that starting point, hunting for the absolute bottom of the valley, the lowest possible error. And how fast you take those steps down the valley is your learning rate. Now, standard stochastic gradient descent just uses one blanket learning rate for the whole network. But the Atom optimizer? It's a completely different beast. Atom scales learning rates individually, per parameter, based on a decaying average of past gradients. It dynamically adapts, which drastically speeds up how fast you reach the bottom of that curve.
Finally, let's wrap up with Section 5, GPU offloading and memory.
It's honestly so easy to forget just how vast the hardware gap is. Just look at the numbers for a simple tensor matrix addition. Pushing your tensors to the GPU yields nearly a 20 times speed multiplier. 20 times! This is exactly why offloading your heavy mathematical lifting to the graphics card isn't just nice to have, it is absolutely mandatory.
But to actually maximize that screaming GPU speed, you have to feed it right. A lot of people apply random noise to their data sequentially on the CPU during the data loading phase. Don't do this. It creates a massive bottleneck. Instead, wait until the data is batched, push the whole batch to the GPU, and apply your noise as a single bulk matrix operation. Utilizing the GPU for what it's best at, simultaneous matrix math, will literally slash your epoch times.
Of course, GPUs have strictly limited memory. When you inevitably hit an out-of-memory error on a giant architecture, gradient checkpointing is your best friend. It significantly reduces the intermediate state stored in your VRAM during the forward pass. Basically, instead of hoarding everything in memory, it segments the model and just recalculates those segments on the fly during the backward pass. You trade a little bit of compute time to free up a ton of memory, allowing you to push 4 to 10 times larger batch sizes on the exact same hardware. It's almost like magic. Bringing this all full circle, when you visualize the underlying computational graph in TensorBoard, you're seeing the actual physical manifestation of the eager execution engine we've been breaking down today. It's a living, breathing map of tensors, layers, and operations actively spinning up and being tracked dynamically as your data flows through. So, as deep learning models continue to grow infinitely larger and more complex, how will you manage this invisible dance of memory and gradients underneath your code? You now have the raw mechanical blueprint. You understand the memory locks, the gradient accumulation, and the hardware bottlenecks. The real question is, how are you going to apply this under-the-hood knowledge to fuel your next big, deep learning breakthrough? Thanks for diving into PyTorch with me today in this explainer. Keep experimenting and keep building.